Comparing an airfoil to a cylinder undergoing the Magnus effect. By rellimgas. The Magnus effect occurs when a circular object is spinning perpendicular to the free stream velocity. As the fluid flows over the top of the object, due to the no-slip condition at the surface, the fluid is accelerated along the surface and has a delayed separation, causing the fluid to be directed downward. Since there is now a force directing the fluid downward, an equal and opposite force directs the rotating object upward. This is an early plane that utilized the Magnus effect. This is a ship that uses Flettner rotors as sails. Here are some video examples of the Magnus effect in action.
But the drive is engaged. It flies, what? And it doesn't fly. You can't fix it, take it.
It's flying.
Look at it go. It flies horrible. I'm working on it.
Here's one that does not suck. There are multiple reasons why one wouldn't want to fly with Flettner rotors. Instability. High angular momentum. Large magnitude of drag. It is this last one that I'm interested in. I want to see just how much more or less lift and drag is generated for a Flettner rotor when compared to an airfoil. I chose the NACA 2412 airfoil and then based the dimensions off the wing from the Cessna 172 since it was the most manufactured aircraft of all time. I calculated the surface area of the airfoil, then using the same surface area and length, I designed the Flettner rotor. I first tried running the analysis in 3D, but the student license prevented NSYS from making an adequate mesh, so I was forced to 2D. I first tried simulating the boundary layer of the cylinder with a rotating mesh field. I then tried to get away with assuming steady and compressible flow for the air. But this caused the lift generated to oscillate around zero. Here is an animation for velocity magnitude. Notice how the velocity field shifts up and down when in reality for a rotating object, the velocity field should be directed down. The second approach was to simply make the surface of the cylinder itself rotate and hope that a boundary layer naturally forms. This approach assumed that the fluid was both compressible and transient, so the complete set of Navier-Stokes equations, negating the third dimension, was used. For the settings in NSYS, I wanted to have them be the same as the ones in the airfoil tutorial but still transient. The general solver was set to density-based and transient. The viscous model was set to K-omega, 2 with SST. Generally speaking, the BCS are supposed to simulate the conditions for an object traveling at 10 meters per second and is at standard temperature and pressure. I choose implicit for the formulation, green Gauss node based for the gradient, and second order upwind for turbulent kinetic energy and specific dissipation rate. The drag and lift reports were also set up the same way as the airfoil tutorial. The angle of attack was steadily increased, recording the lift and drag at each angle, until the wing had stalled. The rotational velocity of the cylinder was steadily increased, recording the lift and drag at each speed, radians per second, until the increase in lift has stopped, or if it happens when the lift begins to decrease. Here is the velocity magnitude for the airfoil at 1 degree angle of attack. And this is at 24 degrees of angle of attack where it stalled. Here is the cylinder at 1 radian per second. And here is the same cylinder at 50 radians per second. Here are the results from hours and hours of iterations. From the table data, it is clear that initially the cylinder has more than a magnitude of drag compared to the airfoil. However, as the drag begins to increase for the airfoil, the drag on the cylinder stays relatively the same, and eventually the lift-to-drag ratio for the cylinder surpasses the airfoil. At first it may seem like using Flettner rotors to lift planes may be worth considering, and while the rotor may have had a greater lift-to-drag ratio at higher speeds, it's worth keeping in mind this analysis didn't take into account how much energy it would require to keep the rotor spinning at 50 radians per second, or roughly 500 revolutions per minute. Also, it's important to keep in mind this is just a simulation and real-world experiments would need to be conducted to validate these findings. Still, though, it shows just how much lift can be generated with the Magnus effect.
I'm working on it.